Greetings everyone and welcome to the channel. My name is Prince Deweyla, and in today's video I'll be introducing you to a new mathematical approach I developed, the Prince square completion method, known as PSCM. This method was created from years of studying how students interact with quadratic equations, the traditional process of completing the square. Through that journey I noticed patterns and simplification that could make the center process more direct, more logic, and much easier to apply, both for learners and educators. Now in this video, I will walk you through the core idea behind PSCM, explaining how it connects to classical algebra and demonstrate why it offers a clear pedagogical advantage over the standard method. So you are a math student, teacher, or simply someone who approaches innovative thinking, stay tuned, because PSCM represents a fresh, modern way of understanding one algebra most fundamental techniques. Now, this specifically was meant for finding the x values of a cubic turning points. But in this video, I'll show you on how you can actually use it. And stay tuned to the very end of the video to learn on how I actually derived this formula. Or comment down below if you do want to learn on how I derived the formula. But for now, specifically the main idea of this video is to dive into understanding how you can apply or use this. For instance, if you are given f of x which is equals to ax cubed plus bx squared plus cx squared plus d, you can actually use this PSCM method to just exactly find the x values of the turning points. Alright, now let's take a look at one example. Now, one of the examples, let's say your f of x is provided to be something of this nature. Let's say maybe 3x cubed plus maybe 2x squared minus, let's say minus 1. Let's say minus 1, or let's say minus 10x in fact, plus 3. Alright, now to find the x values of the turning points, you can simply just write that x equals to, right, now let's substitute the values of a. So the first one is b, so you're going to say negative into 2 plus minus square root of 2 squared minus 3 into the value of a, which is 3, multiplied by the value of c, which is into negative 10 close bracket. Then you can actually create that square root line, leave it there, and then divide everything by 3 into the value of a, which is 3. Now we can simply just punch our calculator. If you do have a calculator with you, you can clearly just do that. Okay, I'm gonna press my calculator this side and give you the values. Unfortunately, I do not have a calculator on the laptop, so let's continue. It's gonna be negative 2 plus minus, right, square root of 2 squared, right, minus 3 into 3 multiplied by negative 10, right, all over 3 into 3, right. Now the first x value of which it gives us where the turning point, you'll have x equals to, the first one is 0.855. so basically that's almost approximately some around 0.86, right, that's about 0.86. and then the second one, the second x value will be then the second value would be at negative 1,299, okay, 5. So which is approximately somewhere around negative 1,30. So let's do the traditional method and see if whether we will still find these two x values for which the turning points will be at. All right, now you know the traditional method is deriving f of x, right? We have 3x cubed, right, plus 2x squared minus 10x plus, how much is the value of d here? The value of d is 3. So you know the first thing is to derive f prime x, right? After you derive f prime x, you're gonna say 3 multiplied by 3, which is 9, right? And then x, take the old exponent, subtract 1, which is gonna be 2. And then you say 2 multiplied by 2, which is plus 4, and then you get x. 2 minus 1 is just 1. Then here it's 1 multiplied by negative 10, which is just negative 10. And you do know that continuing from here, we have to do what? We have to let our first derivative be equals to 0, meaning that the gradient at the turning point is 0. So we're going to say 0 equals to then 9x squared plus 4x plus, not plus, minus 10. Okay, minus 10. And since, well, it does not have factors, you're gonna then use what? You're gonna then use quadratic formula, which is gonna be negative b squared, not negative b squared, I meant to say it's gonna be negative plus minus, right? Negative b plus minus square root of b squared minus 4ac, okay, all over 2a. Now let's substitute the values that we do have right there, okay? When we substitute those values, we're gonna have then negative 9 plus minus square root of 9 squared minus 4a minus 4, and then the value of a, it's just 9 itself. Oh, I made a mistake. The value of a, it's not 9. The value of b is not 9, but rather it's what? The value of b, it's 4. So it's positive 4 right there. And then let's continue with what we had, and then the value of c right here is just negative 10. All right, then we can actually then divide everything by 2 into the value of a, which is 9. So let's take a look at, will we still have the same values? Remember, our x values are the following. We should not forget our x values from above using the PCS and the PSCM, right? So let's take a look at what are the values. Remember this, the values are, we got that there's approximately 0.86 or negative 1.30. So let's punch our calculator on this one and check if whether we get the same answer. Okay, negative 4 plus minus, all right, plus minus square root of 4 squared minus 4 into 9 multiplied by negative 10, right, then over 2 into 9. Okay, so when you press your calculator right there, you get how much? You get the same answer, which is 0.8. You get exactly 0.8555, which is approximately also the same thing, 0.86. And then on this one, same thing applies. You get negative, exactly the same number, nothing like to the dot. You get exactly the same number, negative 9.95, which is exactly also approximately negative 1.30. You get exactly same digits, same interval, like same everything. So you can directly just use this value. You can directly use this formula of my own, the PSCM, to directly get the x values of the cubic turning point. And there's more to learn about this, which there's something I need to clarify. Okay, Now, with the PSCM, right, with the PSCM, I want you to notice something. It says x equals to, right, x equals negative b plus minus the square root of b squared minus 3ac, okay, all over 3a. Now here we introduce a new discriminant, which is 3, which is not 3, I meant to say it's b squared, okay. We introduce a new discriminant, which is b minus 3ac. And of course, now this has its own conditions. Now you need to know those conditions, which I will layer them out right in this video. To note that if the discriminant is actually greater than 0, then it means the following thing. It means, of course, that the cubic function, all right, the cubic function will be having a local maxima and a local minima. If you were to draw that cubic function, all right, it will have a local maxima and a local minima, all right. And then now another thing is the following thing, all right, which I want to clarify in this case. It's if the discriminant is equals to 0 exactly, that means that the cubic function will in fact have one turning point, okay. It will have one turning point, right, one turning point, which is at the point of inflection, all right. Now another thing that's very interesting, it is the when when the discriminant is less than 0. Now when it's less than 0, that means the cubic function will forever be increasing. Now there's more that I'm going to talk about this condition, but for now I'm just going to leave it right here. Just know that it's forever increasing or forever decreasing depending on the value of a. What I mean is that it's forever increasing in a sense that it will create an S shape with a smooth curve, like it's forever increasing or forever decreasing, a smooth S shape. It's forever increasing or forever decreasing. That's something that you should notice, the difference between these two, differentiate between these two. This one has a sharp curve, but it does not have a local maxima and a local minima. But this one has an S shape, but it's forever increasing, a smooth S shape. Okay, now there is more videos that I'm going to actually dive into regarding the discriminant part about it. I'm going to teach you something that I also developed. This is which talks about theorem 1 and theorem number 2 of that part, which is called hidden linearity. There's something I'm going to talk about it, which talks more about monotonicity, and something that's new that you're going to learn. And stay tuned on this video to learn about it. All right, and thank you.